What if the darkest objects in the universe are not lonely at all? What if two black holes, separated by impossible distances, hidden in different regions of space, could still be joined by something stranger than a tunnel, stranger than gravity, stranger than any bridge ever imagined by the human mind? Imagine looking at one black hole on one side of the cosmos, then another black hole far away, perhaps beyond 1 billion stars, and discovering that deep beneath the smooth skin of space-time, they behave as if they are two mouths of the same invisible wound. Not a tunnel you could fly through, not a doorway like science fiction, but a quantum connection so deep that space itself begins to look like an illusion painted over a more ancient reality. Before this journey begins, ask yourself one question and keep it quietly in your mind. If the universe can connect particles across distance through quantum entanglement, then could it also connect black holes across space-time through a hidden bridge? And if this thought pulls you into curiosity, then stay with this story, like the video, subscribe and comment what you believe. Are black holes truly separate objects, or are they secret stitches in the fabric of reality? The mystery begins with something that sounds impossible. A bridge between two black holes should not exist, at least not in any ordinary sense. Black holes are supposed to be cosmic prisons. They are regions where gravity becomes so intense that nothing, not even light, can escape once it crosses the event horizon. If a black hole is a prison, then a bridge between two black holes sounds like a secret passage between two prisons where every door is locked from the inside. General relativity allows mathematical shapes that resemble such bridges, but the same mathematics also warns us that these bridges are unstable. They snap shut too quickly. They collapse before anything can pass. They require strange conditions. They ask for negative energy, exotic matter, and physics we have never controlled on cosmic scales. And yet, when quantum mechanics enters the story, the forbidden bridge returns, not as a simple tunnel, but as something more subtle, a geometry made from entanglement. To understand why this idea is so dangerous and beautiful, one must begin slowly, at the edge of a black hole, where time itself starts to breathe differently. A black hole is not a hole drilled into space. It is not an empty cave. It is a region where mass has curved space-time so severely that all future paths point inward. Outside a black hole, you can choose directions. You can turn left, right, up, down, forward. But inside the event horizon, the future has been tilted toward the center. Falling inward is not just movement through space. It is movement toward an unavoidable tomorrow. The event horizon is not a solid wall. A falling astronaut crossing it might feel nothing special at that exact boundary, especially if the black hole is enormous. But for the outside universe, that crossing becomes a frozen image. The astronaut appears to slow, redshift, fade, and vanish. The black hole keeps its secret, and here lies the first twist. From outside, the black hole looks simple. It can be described by mass, spin, and electric charge. A star, a library, a planet, or 1,000 civilizations could fall into it, and the outside description would become strangely minimal. The details disappear behind the horizon. This is why physicist John Wheeler famously summarized black holes with the phrase that black holes have no hair, meaning they seem to hide or erase all the complex details of what formed them. But quantum mechanics does not like erased information. Quantum theory says that if you know the full state of a system, its evolution should preserve information. It may become scrambled, hidden, impossible to decode in practice, but not truly destroyed. A black hole, however, seems to challenge that sacred rule. The second twist arrives with Stephen Hawking. In the 1970s, Hawking showed that black holes are not perfectly black. Quantum fields near the event horizon can make black holes radiate, extremely slowly, like embers losing heat into the cold universe. This Hawking radiation is not something we have directly observed from astrophysical black holes, because the radiation is far too faint compared with the cosmic background around them. But theoretically, it transformed black holes from eternal prisons into evaporating objects. Given enough time, a black hole can shrink and disappear. Then comes the terrifying question: if everything that fell in was hidden behind the horizon, and the black hole later evaporates into nearly featureless radiation, where did the information go? This is the black hole information paradox, and it is one of the deepest cracks in modern physics. It is not simply a technical problem. It is a warning that our two greatest theories, general relativity and quantum mechanics, do not yet fully understand each other. General relativity says spacetime is smooth and dynamic, shaped by energy and mass. Quantum mechanics says the world is made of states, probabilities, amplitudes, correlations, and information that evolves according to strict rules. Black holes are where these two languages are forced to speak at once, and when they speak, they seem to contradict each other. Now drift backward in imagination, away from the modern paradox to the year 1935. Albert Einstein and Nathan-Rosen studied a peculiar mathematical extension of black hole geometry. They found that the equations of general relativity could describe something like a bridge connecting two separate regions of spacetime. This became known as an Einstein-Rosen bridge. In popular language, it is often called a wormhole. The image is simple but powerful. Instead of traveling across the surface of a long sheet of paper, fold the paper so two distant points touch, then punch a hole through them. The journey becomes short, but this analogy is only a shadow. A real wormhole in relativity is not a tunnel through ordinary space. It is a geometry of spacetime itself. The earliest Einstein-Rosen bridge is not a useful passageway. It pinches off too fast. It is non-traversable. Nothing can pass from one side to the other before the bridge closes. In a realistic collapse that forms a black hole from a dying star, this neat eternal bridge does not appear in the simple way shown in idealized diagrams. The mathematical bridge belongs to a highly symmetric ideal black hole, not necessarily to the messy black holes born from real stars. So already, the bridge seems ghost-like, allowed by equations in one sense, forbidden by physical reality in another. But physics has a strange habit. Ideas that appear dead sometimes return wearing new faces. The bridge was dead as a practical tunnel, but it remained alive as a clue. And in that same year, 1935, Einstein, Boris Podolsky, and Nathan-Rosen published another famous argument, this time about quantum mechanics. They described what later became known as the EPR paradox. They objected to the idea that quantum mechanics could allow particles to be linked in ways that seemed to ignore distance. If two particles interacted and separated, measuring one could instantly tell you something about the other. Einstein disliked this deeply and referred to it as spooky action at a distance. He believed it showed quantum mechanics was incomplete. For decades, the question remained, is entanglement merely ignorance about hidden variables, or is it a real feature of nature? Then John Bell developed a theorem showing that certain hidden variable explanations could be tested. Experiments beginning with Alain Asperger's work and later increasingly refined tests showed that nature violates Bell inequalities. The universe does not behave like a world where particles simply carry pre-written instructions hidden from us. Entanglement is real. It is not a signal traveling faster than light, because it cannot be used to send controllable messages faster than light. But it is a deep correlation that does not fit ordinary classical intuition. Two systems can share one quantum state even when separated by vast distances. Now place these two 1935 ideas side by side. In one paper, Einstein and Rosen described a bridge in spacetime, ER. In another, Einstein, Podolsky, and Rosen described quantum entanglement, EPR. For most of the 20th century, these seem like separate mysteries. One belonged to gravity and geometry. The other belonged to quantum particles and measurement. Then, in the 21st century, Juan Maldacena and Leonard Susskind proposed a bold idea, ER equals EPR. The bridge and the entanglement might not be separate. They might be two descriptions of the same hidden structure. This does not mean every entangled pair of particles contains a little science fiction tunnel that a tiny astronaut could crawl through. It means something more careful and more profound. Entanglement may be related to the connectivity of spacetime. In certain theoretical models, two entangled black holes can be described as connected by a non-traversable wormhole. The bridge is not a shortcut for travel. It is a geometric expression of quantum correlation. The black holes are not exchanging messages faster than light. They are not violating relativity. Instead, their shared quantum state may have a gravitational dual, a hidden geometry joining them. This is where the title becomes alive. The quantum bridge between two black holes that shouldn't exist. It shouldn't exist if we imagine a bridge as an ordinary tunnel through space. It shouldn't exist if we expect classical relativity alone to stabilize it. It shouldn't exist if black holes are only isolated cosmic drains. And yet in quantum gravity, a bridge may exist as a non-traversable structure, a shadow of entanglement, a sign that spacetime is not built from points first, but from relationships. To feel the depth of this idea, imagine two black holes born together in a perfectly entangled state. Perhaps they were created as a pair in an ideal theoretical universe, or perhaps we use them as a thought experiment. Each black hole has an exterior region. Each has an event horizon. To a distant observer, they might appear separated, but mathematically, the complete state may be described as one connected system. The bridge between them is not visible from outside. You cannot shine a flashlight into one black hole and see the other side. You cannot throw a message in and expect it to emerge. The bridge is behind horizons, locked away from ordinary travel. It is like a secret corridor in a dream where every door opens only inward. And yet, even a non-traversable bridge changes how physicists think. It suggests that geometry may arise from information. In ordinary life, distance feels basic. Two objects are near or far. A cup is on a table. A star is light years away. But in quantum gravity, perhaps distance is not the deepest truth. Perhaps what we call space is woven from entanglement patterns. Systems that are highly entangled may be close in a hidden geometric sense, even if they appear far in ordinary space. Systems with little or no entanglement may be disconnected. The universe may not be a stage on which quantum events happen. The stage itself may be made from quantum relationships. This possibility is supported by ideas from holography, especially the ADS/CFT correspondence discovered by Juan Maldacena in 1997. In simplified terms, this correspondence says that a gravitational theory in a certain kind of spacetime can be equivalent to a quantum field theory living on its boundary without gravity. A universe with gravity inside can be described by quantum information on an outer surface. This is called holographic, not because it is fake, but because information in a volume can be encoded on a lower dimensional boundary, like a hologram storing a three-dimensional image on a two-dimensional surface. In this framework, spacetime geometry can emerge from entanglement in the boundary theory. This is not yet a complete description of our real universe, because the best understood version involves anti-de Sitter space, which has different large-scale properties from our observed universe. Our universe appears to have a positive cosmological constant, and resembles de Sitter expansion more than anti-de Sitter geometry. But even if the exact model is not our cosmos, the lesson may be universal. Gravity and spacetime may be encoded in quantum information. Entanglement may be the thread. Wormholes may be the geometry those threads draw. Now the story darkens again. If two black holes are connected by a bridge, what happens when something falls into one? Does it somehow affect the other? Can information move through the wormhole? In the basic ER equals EPR picture, the bridge is non-traversable. Anything that enters one black hole still cannot escape through the other side. The bridge exists, but it does not allow a signal. It is like two people sharing a dream, but unable to use the dream as a telephone. The correlation is real, but communication still obeys the speed limit of light. Then another twist arrived. In 2017, Ping Gao, Daniel Jafferis, and Aaron Wall showed that under special conditions, a wormhole that would normally be non-traversable could become traversable if the two sides were coupled in a particular quantum way. This does not mean we know how to build a cosmic wormhole. It means that in certain theoretical settings, quantum interactions can create the negative energy effect needed to open a passage briefly. The same general kind of strange energy condition is known from quantum effects such as the Casimir effect, where quantum fields between closely spaced conducting plates can produce measurable forces associated with altered vacuum energy. But there is an enormous gap between tiny quantum effects and holding open a black hole-scale bridge. Still, the implication was breathtaking. A wormhole might not merely be a static symbol of entanglement. Under the right theoretical operation, it could become related to quantum teleportation. In quantum teleportation, a quantum state can be transferred from one system to another using shared entanglement plus ordinary classical communication. No matter or energy jumps faster than light. The original state is not copied. It is reconstructed elsewhere after the required classical information arrives. In certain holographic models, this process has a gravitational interpretation, information going through a traversable wormhole. The teleportation protocol and the wormhole journey become two descriptions of one process. This sounds like magic until one remembers that physics often reveals unity beneath difference. Electricity and magnetism were once separate. Maxwell showed they are one electromagnetic field. Space and time were once separate. Einstein showed they are spacetime. Matter and energy were once separate. Relativity connected them through E=mc². Perhaps entanglement and geometry are another pair waiting to be unified. Perhaps a wormhole is what entanglement looks like when gravity is allowed to speak. But the universe does not give its secrets cheaply. For every beautiful idea, there is a warning. ER=EPR remains a conjecture, not a proven law of nature in all circumstances. The black hole bridges discussed in these theories are usually not the kind found around actual astrophysical black holes observed by telescopes. They arise in idealized models, often involving eternal black holes or holographic dualities. Real black holes are messy. They form from collapsing stars, merge violently, spin rapidly, accrete plasma, launch jets, and live in galaxies full of magnetic fields and radiation. We have evidence for black holes through stellar orbits, X-ray binaries, gravitational waves, and event horizon telescope images, but we do not have direct evidence that real black holes are connected by wormholes. That honesty makes the mystery stronger, not weaker. The bridge is not a cheap fantasy. It is a mathematical possibility born from serious attempts to reconcile gravity and quantum mechanics. It lives at the border between known physics and unfinished theory. It teaches us where our understanding bends, where it cracks, where it might become something larger. Now imagine falling toward a black hole in a silent spacecraft. The stars behind you distort into arcs. Light from the universe bends around the hole. The black disk grows not as an object but as a region missing from the sky. Around it, a bright ring may appear if hot gas is orbiting nearby. Time outside seems to accelerate from your perspective. Distant events become compressed, but the event horizon itself may not be a fiery wall in classical general relativity. You cross it quietly. No alarm sounds from space-time. The true danger is deeper, where tidal forces grow and known physics eventually fails. Inside, every path leads inward. Could there be a bridge? In the eternal black hole solution, the interior geometry contains regions that look like another exterior universe. But this is not a stable highway. The bridge pinches off. You cannot turn around and send a postcard. You cannot use it to escape. The mathematics allows a connection, but the causal structure denies travel. This is the haunting nature of non-traversable wormholes. They connect without allowing crossing. They join without opening. Now shift from the falling astronaut to the quantum physicist watching from outside. The physicist does not describe the black hole merely by smooth geometry. They describe quantum states. A black hole has entropy, enormous entropy, proportional not to its volume but to the area of its event horizon. This is the Bekenstein-Hawking entropy. It tells us that black holes store information in a way that is deeply holographic. The number of possible internal states grows with surface area. This was one of the first hints that space-time and information are married at the horizon. Entropy is often described as disorder, but in this context it is more precise to think of it as hidden microscopic information. A black hole with a certain mass, spin and charge may look simple from outside, but it can correspond to a vast number of possible quantum microstates. The event horizon is like a smooth mask hiding an unimaginable complexity. When two black holes are entangled, their combined entropy and correlations may shape the bridge between them. The bridge length may be related to the complexity of the entangled state. As time passes, the interior geometry can grow, even while the exterior black holes look unchanged. This is another strange insight. A black hole can appear stable outside while its hidden interior becomes more complex. Some physicists have connected this growth to quantum computational complexity. Complexity measures how difficult it is to build a quantum state from simple ingredients. In holographic theories, the growth of the wormhole interior may correspond to the growth of complexity in the quantum state. The bridge becomes not just a place but a computation. The interior of a black hole may be the geometric face of quantum complexity evolving through time. If this is true, then the universe is not merely made of particles and fields. It is also made of information processing at the deepest level. The idea is almost impossible to visualize, but try softly. Imagine the quantum state of two black holes as a vast, dark ocean of possibilities. Entanglement is not a rope stretched between them. It is a shared pattern, a single wave function describing both. As time evolves, that pattern becomes more intricate. In the gravitational picture, the bridge behind the horizon stretches and grows. No one outside sees it. No traveler can cross it in the ordinary non-traversable case. Yet the hidden geometry changes. The black holes are like two quiet mouths on the surface of reality, while beneath them, an invisible throat deepens into the dark. This brings us to one of the most dramatic puzzles, the firewall paradox. According to quantum theory, Hawking radiation emitted by an old black hole should be entangled with radiation emitted earlier if information is preserved. But quantum field theory near the horizon also suggests that outgoing radiation should be entangled with interior modes just behind the horizon. A principle called monogamy of entanglement says a quantum system cannot be maximally entangled with two independent systems at once. Something seems to break. Either information is lost, or the horizon is not smooth, or our understanding of locality fails. Some proposed that an old black hole might have a firewall, a high-energy barrier at the horizon that burns in falling observers. That would violate the equivalence principle, expectation of smooth crossing for large black holes. ER equals EPR offered a different intuition. Perhaps the entanglement between a black hole and its Hawking radiation is geometrically represented by wormhole-like connections. Perhaps the interior is not an independent place in the simple way we imagine. Perhaps the degrees of freedom inside are encoded non-locally in radiation outside. This does not solve every detail by itself, but it gives physicists a new language. The paradox may not require fire at the horizon. It may require a radical rethinking of how space-time locality emerges from entanglement. Then came another major development, the island formula. In recent theoretical work, physicists studying black hole evaporation in simplified models found that the entropy of Hawking radiation follows the Page curve expected if information is preserved. The calculation uses gravitational path integrals and includes regions called islands, parts of the black hole interior that are counted as belonging to the radiation's entanglement wedge. This is technical, but the meaning is astonishing. Information that seems inside the black hole can be encoded in the radiation outside. The boundary between inside and outside becomes subtler than ordinary geometry suggests. The black hole interior may be reconstructed from distant quantum information. This again echoes the bridge. The universe may not respect our naive divisions. Here is outside, there is inside, this is near, that is far. These categories work in daily life, but at the edge of quantum gravity they blur. Entanglement can make one region secretly part of another region's description. A black hole can be both a gravitational object and a quantum code. A wormhole can be both a geometric throat and an entangled state. Reality becomes less like a stage and more like a deep language with many translations. The question then becomes, could two real black holes in the universe be entangled? In principle, any systems that have interacted or share a common origin can be entangled, though environmental interactions quickly spread and scramble entanglement. Black holes formed from stars are not likely to be simple, pure entangled pairs in the elegant theoretical sense. They interact with surrounding matter, radiation, and gravitational fields. But black holes can become entangled with Hawking radiation, with matter that falls in, and with other systems through quantum processes. The clean two-black hole bridge is an ideal model, a way to study principles. The real cosmos may contain much messier versions of quantum gravitational correlations. Could black holes created in the early universe be entangled? It is possible to imagine primordial black holes formed from quantum fluctuations in the early universe, and such objects could carry correlations from their origin. But this remains speculative. We do not have confirmed evidence for primordial black holes as a major population, though they remain candidates in some models for dark matter or early universe phenomena. To stay realistic, one must say, the entangled black hole bridge is a serious theoretical idea, but not an observed astrophysical structure. It is a map of what quantum gravity may allow, not a telescope photograph. And yet, humans have already touched this mystery indirectly through experiments that simulate aspects of it. In 2022, a team using Google's Sycamore quantum processor reported a quantum simulation inspired by traversable wormhole dynamics. The experiment did not create a real wormhole in spacetime. No black hole opened inside a laboratory, no tunnel formed on a chip. Instead, researchers implemented a simplified quantum system whose behavior was related to theoretical models of holographic wormholes and quantum teleportation. The result was controversial in interpretation and limited in scale, but it showed how quantum devices might test mathematical ideas connected to gravity. It was not proof that wormholes exist. It was a tiny echo of a deep correspondence. This distinction matters. A false storyteller might say scientists created a wormhole. A careful storyteller says scientists simulated a quantum system with dynamics analogous to a traversable wormhole in a simplified theoretical model. That second sentence is less explosive but far more beautiful because it shows the true path of science. Reality is not conquered by exaggeration. It is approached by precision. The bridge between two black holes that shouldn't exist is not a fantasy door suddenly opened in a lab. It is an idea so delicate that even its shadow on a quantum computer can make physicists pause. Now let us descend into the word bridge. In ordinary language, a bridge allows crossing. It connects two places by giving travelers a path. But in quantum gravity, a bridge may connect without travel. It may represent shared information, not motion. This is difficult because our minds evolved to understand objects moving through space. We imagine tunnels, roads, doors, rivers. But entanglement is not a road. It is a relation inside the quantum state. A better metaphor might be music. Two notes played far apart can belong to the same chord. The chord is not located only at one note or the other. It is a structure of relationship. Entangled black holes may be like cosmic notes in a single hidden chord. The wormhole is the geometry of that chord. The deepest question is whether spacetime itself is the music rather than the room in which music plays. If entanglement builds space, then removing entanglement could tear space apart. In some holographic studies, when entanglement between two sides is reduced, the connected geometry can pinch off. The bridge disappears. Connectivity depends on correlation. The fabric of space is not a passive cloth. It is woven by quantum threads. This idea transforms the phrase distant objects. Distant according to what? According to emergent geometry. According to entanglement. According to the hidden code. But there is a danger in going too far. Entanglement does not mean everything is directly connected in a useful or mystical way. Quantum correlations obey exact mathematical rules. They do not allow thoughts to control distant stars. They do not permit faster-than-light messaging. They do not turn the universe into magic. The wonder is stronger when kept real. Entanglement is not fantasy. It is tested physics. Wormhole geometry as entanglement is not confirmed for our universe. It is a powerful theoretical bridge. The boundary between fact and possibility must remain clear, because that boundary is where honest awe lives. Now imagine the first black hole ever formed in the universe. Perhaps it was born from the death of a massive star, or perhaps from dense fluctuations in the early cosmos. Around it, space-time curved sharply. Matter fell inward. Light bent. The horizon formed like a one-way membrane. Somewhere else, another black hole formed. Could their histories be independent? Maybe. Could their quantum states be connected through ancient correlations from the early universe? Possibly, in subtle ways. But the kind of clean quantum bridge physicists study would require a very special entangled state. Nature may create such states rarely, or not at all on macroscopic scales. Still, the mathematics tells us that if such entanglement exists in the right form, geometry may follow. This is why black holes are the perfect laboratories of thought. They compress contradictions until theories cannot hide. A normal planet does not force quantum mechanics and gravity into direct war. A black hole does. Its entropy is quantum, its horizon is relativistic, its evaporation is quantum field theory and curved space-time. Its singularity is a place where classical gravity predicts its own failure. Its information paradox asks whether time evolution itself survives. If a bridge exists anywhere in theory, black holes are where it would reveal its meaning. But what is inside a black hole? Classical general relativity predicts a singularity, a region where curvature becomes infinite and equations break down. Most physicists do not believe actual physical infinities are the final answer. Instead, A singularity signals that the theory is incomplete. Quantum gravity should replace the singularity with something else, but we do not yet know what. String theory, loop quantum gravity, holography, and other approaches offer different possibilities. The black hole interior remains one of the most hidden territories in science. No signal can come directly from inside an event horizon to tell us what is there. If the ER equals EPR idea is right, then the interior may be less independent than it seems. The inside of a black hole connected to another system might be encoded in entanglement with that system. The bridge might not be a place in the usual sense, but a representation of how information is shared. This challenges the simple image of a singular point at the center. Perhaps the inside is a quantum error-correcting code. In holography, bulk spacetime regions can be reconstructed from boundary quantum information in ways similar to error correction. This means the same interior information may be redundantly encoded in different parts of the boundary. Reality protects its secrets like a code protecting data from damage. Quantum error correction sounds technical, but its role is poetic. In ordinary computers, error correction allows information to survive noise by spreading it across many bits. In holographic quantum gravity, spacetime itself may survive because information is encoded non-locally. Local bulk regions emerge from distributed boundary data. This helps explain how smooth geometry can arise from quantum systems that have no obvious gravity. It also suggests why black hole information might not be lost. The information is not sitting in one simple place. It is scrambled across correlations. Scrambling is another key word. Black holes are thought to be among the fastest scramblers in nature. When information falls into a black hole, it becomes mixed into the black hole's microscopic degrees of freedom extremely efficiently. To outside observers, recovering it would require decoding a fantastically complex quantum state. The information is not destroyed if unitarity holds, but it is hidden beyond practical reach. A black hole is like a cosmic encryption machine. The bridge, if present, is not a simple path through the encryption. It is the geometric shadow of the encryption itself. This leads to the Hayden Preskill thought experiment. If a black hole is old enough and maximally entangled with its Hawking radiation, then new information thrown into it may be recoverable from later radiation after a relatively short scrambling time, at least in principle, if one has access to the earlier radiation and an impossibly powerful decoder. This result made black holes look less like destroyers and more like mirrors, but mirrors so scrambled that no ordinary being could read them. In the ER equals EPR picture, an old black hole entangled with radiation might have a complicated wormhole-like connection to that radiation. The radiation is not a black hole mouth in any simple visual sense, but the entanglement may have geometric meaning in the right theory. Now pause and feel the strange reversal. We began with black holes as places where information disappears. Now they appear as objects whose hidden interiors may be built from information. We began with wormholes as impossible tunnels. Now they appear as translations of entanglement. We began with distance as fundamental. Now distance may emerge from connection. Every step does not remove mystery, it deepens it. The universe does not become less strange when science explains it. It becomes strange in a disciplined way. Could a civilization ever use such a bridge? With known physics, not in any practical sense. A traversable wormhole large enough for a spacecraft would require conditions far beyond anything we can create. Negative energy in the necessary amount and configuration is not something available like fuel. Quantum inequalities may severely limit how much negative energy can be concentrated and for how long. Even if microscopic traversable effects exist in theoretical models, scaling them to cosmic travel is another matter entirely. Black holes themselves are deadly environments. Accretion disks can be hotter than stars. Tidal forces can rip matter apart. Radiation can sterilize worlds. A bridge between black holes, if real in the ER equals EPR sense, is not a highway for humans. But human travel is not the only question. The deeper question is whether nature uses such bridges to preserve consistency. Maybe wormholes are not for crossing, maybe they are for bookkeeping. They allow quantum gravity to keep track of information. They help the universe avoid contradictions. They are not subway tunnels, they are hidden equations of reality. The bridge exists not to let astronauts pass, but to let physics remain whole. This is an important emotional twist. Humans often ask the universe, can we go there? But sometimes the universe answers, this is not about your journey through space. This is about the structure that allows space to exist. The quantum bridge between two black holes may never carry a ship. It may never appear in a telescope. It may never become a portal. Yet it may reveal why space-time is connected, why information survives, why black holes do not break quantum mechanics, and why geometry may be born from entanglement. Let us return to the event horizon. The horizon is a boundary, but not a wall. It is defined globally by causal structure, the region beyond which signals cannot escape to infinity. A local observer crossing a large horizon may not detect anything special at that instant. But quantum mechanically, the horizon is associated with entropy and temperature. This dual nature is strange. How can a place be both locally ordinary and globally profound? The answer may be that the horizon is not made of physical material like a membrane, but for outside observers it behaves like one. It has temperature, entropy, and dynamics. This membrane paradigm helps physicists calculate black hole behavior from outside, even while the true interior remains hidden. If two horizons are entangled, their relationship may define a shared interior. The wormhole is not added to the black holes like a pipe. It is part of the complete space-time description of their joint state. This means the same black hole exterior could correspond to different interiors depending on entanglement. Geometry is state-dependent. The inside is not determined solely by what the outside looks like classically. The quantum state matters. This is difficult because general relativity teaches us geometry responds to energy and momentum, while quantum gravity suggests geometry also responds to entanglement structure. Think of two identical-looking books. Their covers are the same, their weight is the same, their pages look similar from the outside. But one book contains a hidden story written in invisible ink that only appears when paired with another book. The black hole exterior is the cover. The entanglement is the invisible ink. The bridge is the hidden story that only exists in the joint description. Now consider black hole mergers, the events LIGO and Virgo have detected through gravitational waves. When two black holes spiral together, they radiate ripples in space-time and finally merge into a larger black hole. This is not the same as two entangled black holes connected by a stable ER bridge. A merger is a violent classical process where horizons join in ordinary space-time. Gravitational waves carry energy away. The final black hole rings down like a bell. These observations strongly support general relativity in the strong field regime. But they do not tell us directly about wormholes or entanglement bridges. Still, they remind us that black holes are real, not mathematical decorations. The objects at the center of these paradoxes exist in the universe. The Event Horizon Telescope gave humanity images of the shadow regions around supermassive black holes in M87 and the Milky Way's Sagittarius A star. These images are not photographs of the event horizon itself, but of glowing plasma shaped by extreme gravity near the black hole. They show a bright ring and dark central shadow, consistent with general relativity. Again, no wormhole is seen. But every real black hole observed strengthens the importance of understanding what black holes truly are. The quantum bridge idea lives not because we have seen such a bridge, but because the real existence of black holes forces the theoretical question to matter. What would evidence for a wormhole look like? Some speculative studies ask whether traversable wormholes or exotic compact objects could produce gravitational lensing patterns, unusual echoes in gravitational waves, or deviations from black hole shadows. But no confirmed observation has shown this. Most astrophysical data are consistent with black holes described by general relativity. If wormholes exist, they may be rare, microscopic, unstable, hidden behind horizons, or only meaningful as quantum dual descriptions rather than classical objects. The honest answer is that we do not know. And this ignorance is not emptiness. It is a frontier. Science advances by making ignorance precise. We know black holes have entropy. We know quantum theory preserves information in ordinary circumstances. We know general relativity predicts horizons and singularities. We know Hawking radiation should occur theoretically. We know entanglement is real. We know holographic models connect entanglement and geometry. We know ER equals EPR is a serious conjecture. We do not know how all of this becomes the exact physics of our universe. That boundary is where the quantum bridge glows like a distant signal. Now let us imagine the bridge itself, not as science fiction, but as a meditative scientific image. Two black holes hang in separate darkness. Around each, light bends into rings. Time slows near each horizon. Matter approaching them becomes stretched, heated, and lost. To the outside universe, they are separate, but in the full quantum description, their states are woven together. Behind the horizons, the geometry does not end immediately at isolated interiors. Instead, a shared throat extends between them, not through the space outside, but through the hidden structure of spacetime. The throat cannot be crossed. It closes against signals, but its existence means separation was never absolute. In one view, the bridge grows longer with time, not longer in ordinary external distance, but in interior geometry. The black holes remain where they are outside, but behind the horizons, the connecting region stretches. This is deeply counterintuitive. We think interiors must fit inside exteriors, but in general relativity, volumes inside horizons can behave strangely. The inside of a black hole can have enormous volume, even while the horizon area is finite. Geometry is not constrained by everyday spatial intuition. The hidden interior may be vast. This gives black holes a dreamlike quality. From outside, a black hole can be described by a finite surface area. Inside, the geometry may contain enormous depth. From outside, it is quiet. Inside, time and space exchange roles. From outside, it is simple. Inside, it may be complex beyond imagination. From outside, two black holes may be far apart. Inside the quantum description, they may share a bridge. The universe hides depth behind surfaces. The surface area law of black hole entropy was one of the great clues. In ordinary systems, entropy often scales with volume. More volume means more possible microscopic arrangements, but black hole entropy scales with horizon area. This suggests that the degrees of freedom of a gravitational region may live on its boundary. The holographic principle emerged from this realization. If the information content of a region is bounded by area, then spacetime may be fundamentally encoded on surfaces. A wormhole connecting black holes may be another expression of how boundaries encode interiors. The phrase "shouldn't exist" also points to the energy conditions of general relativity. Classical matter with positive energy tends to focus light rays and make wormholes collapse. To hold a wormhole open, one typically needs violations of certain energy conditions, meaning negative energy density relative to the vacuum. Quantum field theory allows small local violations, but not freely or without limits. This is why stable traversable wormholes remain extremely speculative. The universe seems to protect causality. If you could build arbitrary wormholes, you might create time machines, close time-like curves and paradoxes. Physics may prevent such structures through chronology protection or quantum constraints. But non-traversable wormholes are safer. They connect without permitting causal paradoxes. They do not let messages outrun light. They do not create easy time machines. They are like hidden correlations in the book of reality. They can exist mathematically without breaking causality. This is why ER equals EPR is so attractive. It allows bridges, but not fantasy violations. It preserves the strangeness while respecting the rules. The bridge also changes how we think about black hole complementarity. According to complementarity, different observers may describe events near a black hole differently, but no single observer sees a contradiction. From the outside, information may be absorbed and later re-emitted in Hawking radiation. From the inside, an infalling observer experiences smooth passage through the horizon. These descriptions cannot be compared directly, because no observer can access both copies of information. The firewall paradox challenge whether complementarity can work for old black holes. ER equals EPR may help by suggesting that entanglement creates geometric connections that modify how interior and exterior descriptions fit together. This is not settled. There are debates about state dependence, reconstruction, replica wormholes, islands, complexity, and the exact meaning of the black hole interior. But the direction is clear. The old picture of black holes as simple bottomless pits is gone. A black hole is now a thermodynamic object, a quantum information processor, a gravitational geometry, a holographic code, and perhaps one mouth of a non-traversable bridge. Let us bring the idea closer to human intuition. Suppose two people each hold one half of a pair of entangled particles. When one measures their particle, the result is correlated with the other's result. But neither person can choose the outcome to send a message. They must later compare results through ordinary communication to see the correlation. Entanglement is real but not communicative by itself. Now replace particles with black holes. Their entanglement may correspond to a wormhole, but that wormhole is not communicative by itself. To make it traversable in special models, one must add an interaction between the two sides, analogous to the classical communication needed in teleportation. Even then, no faster-than-light travel occurs. The process respects causality. This connection between teleportation and traversable wormholes is one of the most elegant insights in modern theory. In ordinary quantum language, teleportation uses entanglement and classical bits to transfer a state. In gravitational language, the state travels through an opened wormhole. Neither description is more magical than the other. They are dual. The same process wears two masks. One mask is quantum information, the other is spacetime geometry. This duality suggests that what we call movement through space may sometimes be another way of describing information transfer through entanglement. But why black holes specifically? Because black holes are maximally dense information systems. They saturate entropy bounds, they thermalize rapidly, they scramble information, they have horizons. They are gravitational objects whose quantum description is unavoidable. If space-time emerges from entanglement, black holes are where the emergence is most intense. A pair of entangled black holes is like a magnifying glass placed over the connection between quantum theory and geometry. Now, gently, consider the possibility that our entire universe has a similar hidden structure. Not that every star is connected by a usable wormhole, but that the fabric of space is held together by entanglement. In the early universe, quantum fluctuations were stretched by cosmic inflation, seeding the large-scale structure of galaxies. The cosmic microwave background preserves tiny temperature variations from the young universe. These variations reflect quantum origins amplified to cosmic scale. Already, the universe tells us that quantum effects can become cosmic architecture. Perhaps the geometry of space itself has quantum roots too. The universe began in an extremely hot, dense state. Our current theories cannot describe the earliest moment with certainty because quantum gravity is needed. If space-time is emergent, then asking what happened before space-time may be like asking what is north of the North Pole, or what a wave did before the ocean existed. The quantum bridge between black holes points toward this deeper question. Maybe space-time is not the starting ingredient. Maybe it is the result of entanglement patterns in a more fundamental quantum reality. This does not mean the universe is unreal. Emergent things are real. Temperature emerges from molecular motion, but temperature is real. Sound emerges from air pressure waves, but sound is real. A table's solidity emerges from electromagnetic forces and quantum rules, but the table is real. If space-time emerges from entanglement, space-time is still real. It is simply not fundamental in the way we once thought. It is a collective behavior of deeper degrees of freedom. The bridge between black holes is then not an exception to reality. It is a clue to reality's construction. It says, look beneath distance, look beneath geometry, look beneath the smooth continuum. There may be a network of quantum correlations from which nearness, separation, inside, outside, and connection arise. Two black holes connected by a bridge that shouldn't exist may be teaching us that existence itself has layers. Now let us return to the phrase quantum bridge. It is not built from metal, it is not held by pillars, it is not illuminated by stars, it is built from a shared quantum state. Its architecture is entanglement, its walls are geometry, its locked doors are horizons, its silence is causality. It is not a passage for light, yet it is connected to the deepest behavior of light near horizons. It is not a communication channel, yet it may explain how information survives. It is not observed, yet it emerges naturally in some of the most respected theoretical frameworks we have. The human mind wants to ask what it looks like, but perhaps no eye could ever see it, because seeing requires light escaping to an observer, and the bridge lies behind horizons or inside dual descriptions. If a bridge is non-traversable, it is not part of the visible exterior. It is a hidden relation. Asking what it looks like may be like asking what a mathematical equation smells like. The right description is not visual but structural. Still, imagination helps. We can picture two black spheres in an ocean of curved space-time, joined below the surface by a throat no ship can enter. The image is incomplete, but it carries the feeling. There is also a moral lesson in this science. The universe does not always separate things the way our senses do. Two objects can be distant and still correlated. A surface can hide a volume. A horizon can be empty for one observer and thermodynamic for another. A black hole can be a prison and a quantum system. A wormhole can be impossible as a tunnel and meaningful as entanglement. Reality is not obligated to fit one metaphor. This is why the story is full of twists. First, black holes destroy information. Then quantum mechanics says they cannot. First, wormholes collapse. Then entanglement gives them new meaning. First, horizons trap everything. Then Hawking radiation lets black holes evaporate. First, evaporation loses information. Then holography suggests information escapes in scrambled form. First, two black holes are separate. Then ER equals EPR suggests they may be connected. First, the bridge is useless for travel. Then traversable wormhole models connect it to teleportation. First, a lab cannot create gravity's tunnel. Then a quantum computer simulates a tiny analog of the idea. Every answer becomes a doorway to a deeper question. But we must keep one hand on the ground. No one has observed a quantum bridge between real black holes. No spacecraft has entered a wormhole. No experiment has opened a space-time tunnel. The scientific status is theoretical. Strong mathematics, deep consistency arguments, and model-based results support the idea as a possible feature of quantum gravity. But nature has not yet confirmed it in the sky. This honesty does not kill the wonder. It protects it from becoming noise. If tomorrow astronomers found an object behaving unlike a black hole, perhaps with strange lensing or gravitational wave echoes, scientists would study it carefully. Most unusual signals would likely have ordinary explanations first. Matter around black holes, measurement noise, complex plasma physics, or modeling uncertainty. Extraordinary claims require extraordinary evidence. A real traversable wormhole would be among the most extraordinary discoveries in history. Until then, the quantum bridge remains a theoretical lighthouse. Yet theoretical lighthouses matter. Einstein predicted gravitational waves a century before direct detection. Black holes themselves were once considered mathematical curiosities. The positron was predicted before discovery. The Higgs boson was theoretical for decades. Not every beautiful theory becomes reality, but many realities first appear as equations. The quantum bridge may be a future discovery, or it may remain a tool that helps us understand quantum gravity without existing as an astrophysical object. Either outcome would be meaningful. Now imagine the universe after an almost unimaginable time. Stars have burned out, galaxies have faded, black holes remain as some of the last major structures. Over timescales vastly longer than the current age of the universe, Hawking radiation slowly drains them. A stellar mass black hole would take far longer than the present cosmic age to evaporate. Supermassive black holes would take even longer. In that remote future, if our theories are right, black holes will whisper themselves away into radiation. The information they swallowed may be encoded in that radiation in a form almost impossible to decode. The bridges, the entanglements, the hidden interiors may dissolve into the final quantum state of the cosmos. This future image is quiet and haunting. A black hole, once the symbol of absolute darkness, becomes a temporary knot in space-time. It forms, grows, scrambles, radiates, and disappears. If information survives, then nothing is truly erased, only transformed. The bridge between black holes may be part of the mechanism by which the universe refuses to forget. There is a deep comfort in that thought. Not emotional comfort in a simple human sense, but intellectual comfort. The laws of nature may be consistent even at their most extreme. The black hole does not have to be a tear in reality, it may be a teacher. The paradox is not a failure, it is a signpost. It points toward a wider theory where geometry and quantum information are one. But what would that wider theory look like? We do not know. String theory offers one path, where black hole microstates can sometimes be counted, and holography becomes precise in certain spacetimes. Loop quantum gravity offers another path, where spacetime geometry is quantized in a different way. Other approaches explore causal sets, asymptotic safety, emergent gravity, tensor networks, quantum information, and more. No single theory has yet been universally confirmed by experiment. Quantum gravity remains unfinished. The bridge is part of this unfinished cathedral, tensor networks provide a useful analogy. In quantum many-body physics, tensor networks represent complicated, entangled states using networks of mathematical objects. Some tensor network geometries resemble curved spaces. In holographic contexts, they help illustrate how entanglement can create an emergent spatial direction. This does not prove the universe is literally a tensor network, but it gives a visual and mathematical model for how connectivity can arise from entanglement. In such pictures, cutting bonds reduces entanglement and can separate regions. Building bonds creates geometry. The bridge between black holes becomes one dramatic version of a general principle. Connectivity is information. This principle may reach beyond black holes. In condensed matter physics, entanglement patterns classify phases of matter. In quantum computing, entanglement is a resource. In quantum field theory, vacuum entanglement exists even in empty space, connecting neighboring regions. The vacuum is not truly empty, it is a structured quantum state. Perhaps the smoothness of space depends on the vacuum's entanglement. Remove or alter it, and geometry changes. A black hole, with its horizon and entropy, exposes this hidden architecture. The vacuum near a horizon is especially subtle. Hawking radiation can be understood in one picture as arising because the definition of particles differs for observers near the horizon and far away. Quantum fields in curved space-time do not have a single universal particle concept. What one observer calls vacuum, another may perceive as radiation. This tells us that even emptiness is observer-dependent in gravity. The black hole forces us to abandon simple absolutes. If the bridge is real in a quantum sense, then the interior may also be observer-dependent or code-dependent. Different reconstructions may describe the same underlying quantum state. This is not saying reality is subjective in a loose way. It is saying that in quantum gravity, the mapping between quantum information and space-time geometry may depend on what system is accessible and what questions are asked. This is precise, not mystical. The same underlying state can have different complementary descriptions. The more we study black holes, the more the word information becomes unavoidable. Information is not just human knowledge. It is the distinguishability of physical states. It is what makes one arrangement different from another. Quantum information includes amplitudes and phases, not merely classical bits. When a black hole swallows a diary, the human-readable words vanish behind the horizon, but the quantum information describing the diary's particles should remain in the universal wave function. The paradox asks how. One possible answer is that the information is encoded in subtle correlations in Hawking radiation. Early Hawking's original calculations seem to produce thermal radiation independent of the details of what fell in. But later insights suggest that non-perturbative quantum gravitational effects may restore correlations. The radiation may look thermal approximately, but not exactly. Tiny deviations, spread across enormous time and many particles, could carry the information. To recover it would be almost impossible, but the laws would remain unitary. The bridge helps us visualize how information that seems lost inside might be connected to outside degrees of freedom. But we must remember that visualization is not the proof. The proof, where it exists in simplified models, comes from mathematics, entropy calculations, replica wormholes, holographic reconstruction, quantum extremal surfaces, and consistency with the page curve. These are not easy ideas, but their emotional message is simple. The black hole may not destroy the book, it shreds it into quantum letters and scatters them through radiation, while the dictionary needed to read them is hidden in entanglement. Now let us consider what happens if two entangled black holes are separated by a vast distance. Does the bridge length depend on that distance? In the exterior space-time, they may be far apart. In the interior wormhole geometry, the relation is different. The bridge is not embedded in the exterior space like a subway tunnel under a city. It is its own space-time connection behind horizons. This is why the paper-folding analogy can mislead. A wormhole does not necessarily run through the space between objects. It changes the topology or geometry of space-time itself. Topology is the study of shape in a deep sense, how spaces are connected, whether they have holes, handles, or separate components. General relativity allows space-time topologies and equations, but quantum gravity may constrain which topologies are physically allowed. Wormholes raise questions about topology change, causality, and path integrals. In gravitational path integral approaches, Summing over geometries can include wormhole contributions. These can affect calculations of entropy and correlations. Again, the bridge appears not as a traveler's path, but as a contribution to the quantum structure of gravity. Some wormholes, in theory, connect different universes rather than distant regions of the same universe. This leads to speculation about baby universes and multiverse-like structures. But here, caution is essential. Such ideas are mathematically explored, not empirically established. For this documentary, the grounded focus remains on entangled black holes and non-traversable or theoretically traversable wormholes in quantum gravity models. The goal is not to invent universes without evidence, but to understand why bridges appear in serious physics at all. Why does nature hide the bridge behind horizons? Perhaps because horizons are where causality protects the outside world. A non-traversable bridge can connect without allowing paradox. It is like a private correlation that cannot be weaponized into faster-than-light messaging. Quantum mechanics also has this character. Entanglement is powerful, but no signaling protects relativity. The universe permits deep, non-local correlations, while forbidding controllable superluminal communication. ER equals EPR extends this balance into geometry. Wormholes may exist but remain non-traversable unless special interactions are added that still obey causal rules. This balance between freedom and restriction is one of physics' great themes. Particles can be in superposition, but measurement outcomes follow probabilities. Light speed limits signals, but spacetime can expand so distant galaxies recede faster than light due to cosmic expansion, without locally violating relativity. Black holes trap light, but radiate quantum mechanically. Wormholes may connect regions, but not allow easy travel. Reality is not simple, but it is disciplined. Now imagine explaining this to someone standing under a night sky. Above them are stars, planets, nebulae, galaxies. None of the quantum bridge is visible, yet the same universe that paints the sky also obeys quantum rules at its deepest level. The atoms in their body are quantum systems. The light entering their eyes is made of photons. The gravity holding their feet to Earth is space-time curvature. Black holes are not separate from human reality. They are extreme versions of the laws already operating everywhere. The bridge between black holes is not a random fantasy. It is a question forced upon us by the same physics that lets atoms exist and stars shine. There is also a connection to the mystery of why atoms are stable. Electrons do not spiral into nuclei because quantum mechanics gives them discrete states and wave-like behavior. Matter feels solid because of electromagnetic forces and the Pauli exclusion principle. Light behaves as both particle and wave. Empty space has quantum fluctuations. Every ordinary thing is already strange. Black holes simply turn the volume of strangeness to maximum. They make the hidden rules visible by pushing them to extremes. The bridge is therefore not an isolated curiosity. It is part of a larger revolution in which information becomes physical. Landauer taught that erasing information has thermodynamic cost. Black hole entropy showed that information and gravity are connected. Quantum computing showed that information can be processed in ways impossible classically. Holography suggested spacetime can be encoded. ER equals EPR suggested entanglement can be geometry. Step by step, information moved from being something humans know to something the universe is. Can there be a bridge between two black holes that should not exist? The answer depends on what exist means. If it means a visible tunnel through space that spaceships can enter, we have no evidence and strong reasons for skepticism. If it means a non-traversable Einstein-Rosen bridge in an ideal entangled black hole state, then yes, in certain theories it is a valid description. If it means a general principle that entanglement and geometry are deeply linked, then the evidence from holography and black hole information theory is powerful, though not yet a final theory of our universe. The bridge exists at the frontier between established physics and theoretical possibility. This frontier is exactly where curiosity belongs, not in false certainty, not in empty speculation, but in careful wonder. The quantum bridge is a question shaped like a tunnel. It asks whether space is made from entanglement. It asks whether black holes preserve information through hidden correlations. It asks whether the inside of a black hole can be reconstructed from the outside. It asks whether the universe is more connected than distance suggests. It asks whether geometry is the shadow of quantum information. Now let the story slow down. Picture a black hole not as a monster, but as a silent teacher. It does not speak. It does not shine by itself. It simply bends everything around it until the laws of physics reveal their deepest tensions. Around it, stars orbit in obedience to gravity. Gas spirals inward and heats. Light curves. Time dilates. Quantum fields tremble near the horizon. Entropy counts hidden states. Radiation whispers of evaporation. Information refuses to die. And somewhere in the mathematics, a bridge appears. The bridge should not exist because ordinary intuition says two prisons cannot share a secret hallway. It should not exist because classical energy conditions crush wormholes. It should not exist because horizons forbid escape. It should not exist because space says far is far, and yet quantum mechanics says separation is not the whole story. Entanglement says two systems can be one in a deeper sense. Holography says volume can be encoded on surfaces. Black hole entropy says area remembers. Quantum gravity says geometry may be born from information. In that deeper language, the bridge does not merely exist, it becomes almost inevitable as a symbol of hidden unity. But the symbol is not the final answer. The final answer remains unknown. A complete theory of quantum gravity must explain black hole interiors, singularities, evaporation, space-time emergence, cosmology, and observable predictions. It must reduce to general relativity where gravity is classical, and to quantum field theory where space-time is fixed. It must explain why our universe has the properties it has. ER equals EPR may be one piece of that theory, or a clue pointing towards something even stranger. Science is often portrayed as a collection of facts, but at its deepest level it is a disciplined relationship with mystery. The quantum bridge between two black holes is not a fact like the mass of the sun. It is not an observation like gravitational waves. It is a theoretical idea supported by serious mathematics and connected to real paradoxes. Its power is not that it gives us all answers, but that it organizes many questions into one breathtaking possibility. Now, we can ask the central question one last time. Are two entangled black holes connected by a bridge? In the cleanest theoretical models, yes, they can be described that way. Can anything pass through it? Normally, no. Could special quantum interactions make a related wormhole traversable in theory? In certain models, yes, without violating causality. Have we built or observed such a bridge in the real universe? No. Does the idea matter anyway? Deeply, because it may reveal how space-time and quantum information are joined. At the end of this journey, the black holes remain dark, but they are no longer empty darkness. They are full of hidden structure. The bridge remains invisible, but it is no longer meaningless. It is a possible sign that the universe is stitched together beneath the surface. The event horizon remains a boundary, but it is also a place where thermodynamics, quantum theory, and gravity meet. Distance remains real in daily life, but perhaps not fundamental in the deepest theory. The universe remains vast, but perhaps vastness is woven from connection. And so the impossible bridge becomes a quiet revelation. It tells us that what cannot be crossed may still connect. What cannot be seen may still shape reality. What appears separate may be secretly one system. Two black holes divided by cosmic darkness may share a hidden quantum bond. Not a doorway for escape, not a shortcut for conquest, but a bridge of information, a geometry of entanglement, a whisper from the unfinished theory of everything. If there is an amazing result at the end, it is this. Black holes may not be the places where physics dies. They may be the places where physics is reborn. The quantum bridge that shouldn't exist may be the clue that saves both gravity and quantum mechanics from contradiction. It may show that space-time is not the deepest layer of reality, but a beautiful emergent pattern. It may reveal that the universe is less like a collection of isolated objects and more like a hidden web of relationships. And in that web, even the darkest holes may be connected by threads of quantum light too subtle for eyes, too deep for ordinary travel, but powerful enough to reshape our understanding of existence. End.